Our final example is the well-known Hanoi Towers puzzle. In this puzzle, we're given 3 sticks. 2 of them are initially empty. On the first stick, we have n disks, sorted by size as shown here on the slide. Our goal is to move all n disks to some other stick, to one of the 2 empty sticks. This would be easy if not the given 2 constraints. First of all, we are allowed to move only 1 disk at a time. And naturally, we need to take the topmost disk from one stick and to put it to some other stick. Right? And also, we are not allowed to put a larger disk onto a smaller disk. Okay? So the question is whether it is possible for, and if it is possible, then for which values of n this is possible. Okay? So it is known to be possible for every value of n. At the same time, it is not clear at this point how can we be sure that it is possible for every possible value of n. We can check that it is possible for 1, for 2, for 3, for 4, and so on, but it is not so clear how to ensure that just for every even very huge number it is always possible. And of course we are going to use recursion again to show how to do this for every possible value of n. For this, we will first explain that it is possible when n is equal to 1. And then we will show that if it is possible for n minus 1, for example, then it is possible for n. This will ensure that if it is possible for 1, then it is possible for 2. If it is possible for 2, then it is possible for 3. If it is possible for 3, then it is possible for 4, and so on. So our goal is basically to show that it is possible in the beginning when n is equal to 1, and then we need to show some generic procedure of building a solution for n disks using a recursive solution for n minus 1 disks. Okay, so let's start. So the simplest possible case is indeed when there is just one disk. So in this case, n is equal to 1, and our goal is to move this disk to some other place, to some other stick, and of course it is very easy to do this. So we just move it to another stick. Now let's also consider 2 disks, just to get a feeling of how to solve this problem. Now in this case, we first move the smallest disk. So we move it to this stick, then we move the larger disk to another stick, and finally we move the smaller one onto the larger one, right? So for 2 disks it is also possible. Now let's consider a general case where we have n disks, and let's focus on the larger disks, on the larger disk, I'm sorry. So what is the condition under which we can move it? So first of all, if we are moving the larger disks, this actually means that all the remaining n-1 disks are already on some other stick. So probably a part of them are on one disk, and all the remaining of them are on the third stick. I'm sorry. So if we are moving this larger disk, so for which stick we can move it? So I'm claiming that the only stick for which we can move it is the empty stick, right? Because if there are any disks on this stick, then we will violate the rules. If there is at least one disk, I'm sorry, on this stick, then by moving the largest disk to this stick, we will put a larger disk onto a smaller one. So this means that when we are moving the largest disk, we should move it to an empty stick, which in turn means that all the other disks at this point should be should be put to the same stick. And since we know that all the disks are always in increasing order, we know that at this point all the other disks should be located as follows. Right? So when we are moving the larger disk, all the remaining disks should be at some other stick, which means that up to this point we've moved all other n-1 disks. So we actually solved a problem for n minus 1 disks, right? And this gives us an idea for a recursive solution. Because this is essentially the same problem which was solved for n minus 1 disks. So a recursive solution in this case is the following. So we first move n minus 1 disks recursively to some other step. So then we reach the following state. After this, we move the largest disk. Okay? And then finally we move once again the n minus 1 disks, again using a recursive call. Okay, so we know how to do this because we can call the same procedure with parameter n minus 1, and this finally gives us the solution, right? So we reduced the problem with parameter n to the problem with parameter n minus 1. This problem in turn will be reduced to a problem with parameter n minus 2, then with n minus 3, and so on, until we reach 1, and for 1 we know that it is possible, right? So essentially what we've proved is that it is possible for every value of n. We can consider this, for example, like this. We know that it is possible for 1, then it is possible for 2, right? Then, since it is possible for 2, it is also possible for 3, and so on. So it will be possible for all the numbers. Or put it otherwise, to solve the problem for n, we need to solve it for n minus 1. To solve the problem for n minus 1, we need to solve it for n minus 2. Meaning that if we know how to do this for n minus 2, then we definitely know how to do this for n minus 1, and so on. So going backwards, we will reach 1, and for 1, we know that it is possible. So which actually proves that it is possible, and what just happened is that actually we've proved that it is possible by induction, which is a highly related notion to recursion. So saying very roughly, induction is a mathematical method for proving something, while recursion is a method of defining something or a method of implementing something.